Okay, Paul here. Today on the bench we have this cool device. This is a Geiger counter, and it's the way to do the model number on this one is it's a CDV 700 model 6B. So they usually refer to it as a 700 6B. It was made by Victorine Instrument Company of Cleveland, Ohio. It's about a 1962 model. It has a probe that, of course, probes for incoming radiation, headphone jack, and a headphone set so that you can hear the beeps as the ionization process is performed. The way these things work, well, let me undo this probe. Give me a second here and I'll show you. Okay, it has a probe that has a metal case all the way around it. Okay, and the metal case is grounded to the chassis. So any electrons any electrons that hit the case go right to ground and they're not counted. It has a entry port here, which I believe you have to turn this to open. But basically inside is a gas, an inert gas, and the random electromagnetic waves, radiation waves come in through this port, and they're loose electrons. They hit the gas, and they knock electrons free, which creates ions, a positively charged atom and a negatively charged electron. And so as those ions are created, that sends an electron out, and actually I believe the case, it's attracted to the case because the case is connected to ground, so the case is positively charged because all the free electrons go to ground. So they're attracted to the case, and when they go through the meter, and the meter records it as a pulse. And that happens each time an ionization happens. So incoming radiation knocks electrons out of their orbits of the atoms, creating ionization, creating a positive atom and a negative electron. And those negative electrons are captured and recorded as pulses per minute. And the higher the pulses per minute, the more radiation's coming through. Now, misconception that people have about Geiger counters is that when it's going higher, it's higher wavelength radiation. In other words, beta, and then X-ray, and then gamma rays. That's not the case at all. These do not distinguish between any kind of radiation. They just measure the amount or the intensity of the radiation. So it could be really high and be beta, or it could be really high and be X-rays, or be real high and be gamma rays, which is dangerous. And so they made these in the really prevalent in the 60s because it was the atomic age, right? Everybody was building bomb shelters and worrying about radiation. So they started marketing these devices. It is a very good device, very simple made device, and was invented back in the 20s, early 20s, 1920s, and is very effective. But its proliferation came about in the atomic age. And so this is the probe, this is the unit. We're going to open it up and work on it because the owner said that it is not working and that there was some battery corrosion. So that's what we do know about it. And he sent it in to be rewired. So let's take a look at it. Okay, this is the unit and this is the case. Let me set the unit down and we'll take a look at the case first. And you probably see there was a schematic diagram in there. There's a piece left. But the case is full of corroded, rusted metal, and that's where the corrosion from the battery case came. I'll try to get all that out of there so it doesn't do more damage to the inside of this case, and perhaps hit it with a yellow primer and stick a new schematic diagram down there if I'm able to do that. so that it'll be back to, you know, its information. Now, if we look at the Geiger counter, you'll see what happened. This is one of the battery cases, and you see there's some corrosion in here on these terminals. Let me see it there. This is the other battery case, and you can see it suffered major corrosion. The clips are totally gone there. This one's completely gone, that one's gone. But you see this retaining clip that holds this battery case in? Notice, totally rusted away. So that's what's in the bottom. Well, obviously it can't work without this wire, and this clip is fully gone, so we're going to have to figure out how to reinvent the wheel on these battery boxes to recreate these terminals and get these terminals created so that we can connect wires to them, because that's the problem. Now, if you do ever work on one of these, be aware that these things can get way up in voltage, so extremely deadly. Okay, extremely deadly voltages. You do not want to be playing around in here. If you don't know anything about electronics and how to handle high voltage, do not even mess with these things. And I'm going to go ahead and download the documentation, and we'll take a look at that. Here's the red wire that goes to this terminal, totally gone, and the blue wire there on the other side is totally deteriorated. This one's still here, and it's loose on the other side. So let's turn around and take a look at those. Okay, so that red wire comes across from the other side of the battery case over to here, and this blue wire here totally corroded away, and it went here, went to this terminal here. Now this is your calibration controls here. You probably noticed in the case that it's got an operational check source label there. That actually is a radiation source that comes out of, and it actually has beta radiation, a very lower rate, and of course they deteriorate over time, you know, half-life, right? But we don't know how well that is yet, but it should still have some radiation. So anyway, let me get the documentation. We'll take a look at that, and then we'll try to figure out how to fix this battery compartment issue. Okay, working on this Geiger counter, fixing these battery boxes that are all corroded. This one wasn't as bad as the other one, but the terminals are corroded completely away. I started with the worst one, and what I did is I cut this off, this section here, right here. Cut it off with my Dremel, ground it down a little bit, roughed it up some, got some new battery boxes, and what I'm going to do is use a little epoxy and epoxy that right on there. Of course, I'll do that one too once I get this one done. But yeah, that's going to be epoxied right there. If I could use two hands, I could pull that wire through there. So it's going to sit just like that. I was going to use some little screws. I don't have any small enough, and I didn't want them sticking through on this one and hitting the circuit board. Also, I didn't want the heads being in the way of the batteries sitting down in there. So I figured, you know, that was permanently on there. So I'm going to make this one permanently on here with some epoxy. But I'm not going to put a lot. If it ever had to come off, it could be pried off and be sanded in a new box put on. So, you know, these could be replaced. But, yeah. So anyway, now it does sit down a little bit, you know, goes this way in the case. It is a little bit higher or a little bit thicker here than the original, but not by much. I mean, it's just a little bit. And when I put this in the box here, when I put this back in the case comes down about 3/4 of an inch, almost an inch more. So there's plenty of room. It's not a problem. So that was the best fix, and that's what I'm going to do. I'm going to epoxy them on and put them back in here with new boxes. We'll connect the wires, and then we'll check the I'll probably jump the wires in first before I even put them in there, so we can make sure the unit is working correctly. But yeah, so anyway, that's where I'm at on remodeling this Geiger counter. And you never know what you're going to get into, you know, when you're doing this kind of work, but came out pretty neat, nice and smooth, and it'll look good when it's done. So, and it'll be original screws back into the original post. Everything will be great as far as that's concerned, tolerance wise. So yeah, I'm working on this Geiger counter, and I wanted to show you something that I haven't seen before. It's kind of weird. I stripped this wire, getting ready to put the new battery cases back on, and you see the wire is fine. I went to strip the negative terminal wire, and the corrosion is so bad. These are the pieces that I tried to strip off, and notice this dust that's coming out of the insulation. There is no wire left in the insulation. It's totally corroded away. How far back, I don't know. See it? But you can see the stretch marks and white discoloration on the wire. And when I go to strip it, it just breaks off, and the pieces are nothing but empty tubes of corrosion. Look at that. Unreal. I never seen a wire that far gone. Doesn't matter, we got long leads on the battery cables that we're putting in on the battery boxes. And there's the finished box connected to the original plate, so I can screw it right back in. So what I'm going to do is this one connects here, it's soldered here, and I imagine the corrosion ends somewhere around here. See how swollen it is here. So I'm just going to unsolder that and solder the new wire on there. Let me come back, if I can do this with one hand, past where I see the swelling. And I didn't strip it. Yeah, it did. And you see the wire is fine there. Nice copper wire, nothing wrong. But the corrosion is all the way up to about here somewhere. So anyway, something to look for when you're working on these is if there's, or any device where there's corrosion, bad corrosion in the battery box, you may look at the wire and think it's okay, and it could be like that, where it's just totally disintegrated copper. You see the green, it's hard to tell on a blue mat, but it's green tint, and of course that's copper corrosion, right? Turns green. So there's one for the books. Okay, I'm working on this, but I want to document this. This is the black wire, and it goes there, to that terminal there. Red wire here goes to that terminal right there in the middle. Blue wire, which is the, after the 6 volts, goes to that terminal right there, that string. Let's see, what else? This probe wire goes right to the corner here. That's the probe wire. 2 meter wires. The black one goes here. Right there. That's the black meter wire. The red meter wire comes right out to the edge of the board. And that's what we got here. And let's see. Oh, this connector wire here, center wire, comes right to this corner here. And the ground is, the probe is grounded to a box, so I'm assuming that this ground, yeah, right there through that transformer housing, that's ground. So this is ground, and it's to the chassis. Okay, I got my battery packs together here. Got new batteries in it, brand new Duracell copper top batteries, and put it all together, and it's still no worky. And then I did some testing, and I'll show you what I found. These are the battery case screws. I just put them back in finger tight so I wouldn't lose them. So let me take these off. These are some weird screws too. They're self-tapping screws. I don't think they even tapped these holes. They just put the screws in. Anywho, okay, so here's the unit. And what I had figured was I went around and checked the resistors. They were fine. Checked the diodes. They were fine. Capacitors seemed fine. These are nice capacitors. They're solid poly. They're not paper wax. I haven't lifted a leg on this one yet to check it, but I'll do that and make sure that it's correct. So I did all that, and then of course there's two transistors, and I haven't checked those, but I think they're fine. I don't think that was a problem. So my first thought was there's no high voltage because there's no sound. So there should be high voltage. So it would lead me to think that there was no oscillation on the high voltage, and so because that's what makes the clicking, and the way it works is it has this transformer, which is a flyback transformer. So if we look at the schematic, which I have here, okay, let's see, I think okay, this is the schematic. The switch is a two-part switch, actually three-part. It switches this battery to ground, these two batteries, one battery case to ground. It switches these two batteries to this circuit here. This circuit is the circuit in question. This is your high voltage side here. And you should have high voltage across this tube and across these two capacitors. It's got a selenium rectifier instead of a diode. And then here's the other two diodes that I did check. Now the selenium rectifier, I didn't check it. It's high voltage. It'd be hard to check with a multimeter. I take that back. I did check it, and I got a high resistance one way and a open the other way. So I'm assuming it's okay, but it's really hard to check those. And then the other part of the switch here is for the actual setting of the meter, and how sensitive it is, times 1, times 10, times 100, and off. So that's the three parts of the same switch. They work together. Okay. So when this goes to time 1, it's grounded. It goes to time 10, it's grounded. It goes to time 100, it's still grounded. Same thing here, times 1, times 10, times 100. All that does is, no matter where you set the switch, other than off, it's just connecting the battery to this Q2 transistor. And this is where the flyback action happens. This transistor oscillates, and when it oscillates, it sends a signal through here, and then it shuts off. And when it shuts off, the magnetic field here collapses and generates these two magnetic fields collapse across this coil, which generates a spike of high voltage. And so this oscillates on, off, on, off, on, off, and that's what makes this pulse at high voltage, 900 volts or thereabouts. But we're not getting any high voltage. And there's two ways I know. One, there's no sound. Two, there's no evidence of any voltage on this side at all of this transformer, this flyback transformer. The other thing is, it is a flyback transformer, which means if it was pulsating and turning on and off, the iron core would vibrate, and you would actually hear that. You should hear some sound as the core is vibrating, However, whatever frequency it's vibrating at, it's going to be low frequency, probably around 200 hertz. So you ought to be able to hear those laminations in the transformer actually vibrating and clicking against each other. And there's none of that. So what I did is I lifted one end. Well, first I checked the input side of the transformer here for continuity. And sure enough, there's continuity. It's low resistance. So then what I did is I lifted one lead here. So I wanted to take it out of circuit because when I checked it, let me pull a light over here. I checked across there and I was getting bad resistance. I was getting good resistance from here to here, but I was getting bad resistance. Let me see. I'll show you what we got going on here. Let me set up my little, and give me a second to hook up these alligator clips. Okay, so you see I'm across those two. I got 260 ohms, and I was wrong saying that that's the input. That's actually the output. I'm used to seeing two wires on an input on a transformer, right, and a center tap output. But in this case, there's two sections in, and they switch over. They reverse in the schematic, which we've seen. So we got 261 ohms there, so we're okay there. If I go to here, we got an open load. And of course, if we get an open load there, then there's really no sense in checking the center one, because it's open load too, right? It has to be. Already checked it, and it is, of course. but it has to be because there's connectivity between these two. So any one of those to here is irrelevant. You're going to get two different readings if it was good. So the transformer is bad. Now, I only lifted that one, found the problem, and, well, the problem with that part of the circuit. And so you can see it's still the original solder joints. I haven't taken it out. So what I did is I went online and tried to find this transformer. And you can see the number there. It's a 1432. And it has 3, 4, and 5 on this side and 1 and 2 on the other side. And here it is here. So 1 and 2 on that side, on the output side or the high voltage side. This is the input side. So 3 and 4 goes from the emitter through 1 through 3 and 4 to the collector of this PNP transistor. 5 and 6, you don't have 5 and 6, you only have 3, 4, and 5 on the other side of the transformer. The reason is because 6 and 3 are the same. It's the same wire, they just connect together inside the transformer. So on the outside of the transformer you have 3, 4, and 5. Well, 3 and 6 are exactly the same. So on 5 and 6, or 5 and 3, if you want to look at it that way, it goes from the emitter through this 8K resistor, available potentiometer resistor, to the base. And so that's where the signal comes in. So as one comes on and generates a voltage, the voltage goes through, comes around the other one, shuts the transistor off because it puts voltage on the base. Well, first it puts voltage on the base and turns it on, and then the other one conducts, right? And then it puts voltage on the collector that's even with the base and shuts the transistor off, and that's what oscillates back and forth, and that's what makes your oscillation and your high voltage. So the transformer is bad. If we go to the parts list here, you can see that here it is, transformer, flyback transformer. It's a 1432, and that's what it says, 1432. So I went online and I was able to find a transformer. So it came in the mail, and now we can continue working on this. Let me pause this and I'll get it out of the bag and we'll take a look at it. Okay, and here it is, 1432. And this one lets you know that this is 3 and 6, this is 4, and this is 5. 3 and 6 are the same. That one just says 3 and 4 and 5. But it didn't matter, it's the same one. It's 1432, it's a product number of the transformer, or the nomenclature. And so if we check across 3 or 6, whichever you want to call it, to 4, we get 11 ohms, 11.6 ohms. If we go from 3 to 5, which would be the same as 6 to 5, and if I could get the alligator clip to cooperate, we get 5.7 ohms. So the inputs of this transformer are fine. Now if we go to the output side, which would be 1 and 2, and of course, you know, it doesn't matter how you hook these, all right? We've got 3K, sorry, 3.4K. And the one that's in there, though it's in circuit, might be a little different because it's in circuit, but it's about 3K because that's what it's supposed to be. And it's 3.2. So we have the same system here, same transformer to go in. Now the interesting thing to deal with for me is they riveted the case in, and they also got on this tube here, this high voltage indicator light, they have a strap that goes with a wire that goes around the rivet, and it's riveted in too. See that wire there? That wire goes around the rivet. That's ground, but that's why they did it that way. And so they riveted it in. Now, I had two options. One, well, let me get this out of the way. Try to gently flip this over. And see the rivet is soldered, and you know it's the ground line. On the other side of the transformer here, we have just the wing of this transformer case, it screws with a screw into here, so it grounds this to the ground through this. So rather than take that all apart and take the risk of really messing up this board and or this probably irreplaceable corrosion tube, it's a Victor. Well, anyway, I don't want to mess with that. If it's good, it's good. If it's not, oh well, then we got to deal with it. But I'm assuming it's good for right now, and I don't want to make it bad by playing around with trying to drill out a rivet that's soldered to the board and probably mess up the board. So what I'm going to do is just undo this. You know, this is just a case around the lamination of the transformer, and let's see, find a small screwdriver here. You see, it can come off, right? See, it can bend off the transformer. You see what I mean? And so what I'm thinking of doing, because it's just a case around the lamination, if I take that off the transformer, unsolder the transformer, I can put the new transformer in, solder it in, take the case off of it, and then wrap this back down and put the bolt back through, and we got all the grounds in place, and I didn't mess this up. I'll have to unfold it here in order to get the transformer out. But that's probably what I'm going to do. That would be the most logical approach to doing this. And I know I can get another transformer if I mess things up, so it's less likely to be an issue of damaging something this way. And if I do damage something, the only thing I'm going to damage is the transformer, which I can get more. It's replaceable, rather than taking the risk of damaging something that is no longer available. These units are very expensive on the market, and trying to find another unit to get this on, or the high voltage selenium rectifier, it would be too expensive. We're talking, they ask, hundreds for these things, even not working. So I'd rather take the risk with the transformer, and that's what I'm going to do, and redo the casing on it. Not a big deal. And then we should be back in business. At least we should have high voltage at that point, assuming that this switching transistor is okay. And I checked it. It seems okay on the board. I checked the resistance. So I don't think there's a problem there, but I won't know until we put the transformer in. So let me get the transformer in, hook up the batteries, and we'll do another test. And if it's working at that point, then I can let it discharge and get the voltage out of there. And I'll check this capacitor. I'll lift one end of the capacitor and check it and make sure it's okay. I know these guys are going to be fine. They're not a problem. And I'm pretty sure, almost 99.9% sure that guy's okay. But I'm going to check it just to make absolutely sure. And then the transistors, the thing will either work or it won't. If it don't work, then I have to deal with the transistors. If it works, then I know they're good. But, it's like, car don't want to move. You got a flat tire, it's pretty obvious, right? It's the tire is flat, you got to put air in it. Well, it's going to be the same thing. If everything else is fine, then I know the transistors will be within spec. So that's where I'm at. Thanks for watching. Okay, got the transformer soldered in. And who says you can't solder on a PC board with a Weller 140 watt soldering iron? I had no problem. Anywho, okay, so we're going to cut the leads. Okay, so now we're all soldered in. Okay, when I unsoldered the other transformer, this fell off. So apparently it broke off inside the transformer somewhere. And you can see some corrosion in there. See that green? That's, it got corroded somehow. Moisture got in this, probably from the batteries, because again, there was all kinds of battery corrosion everywhere. So, anywho, that's done. And of course I got to clean up my little clippings here, but there's the transformer, and you see the case is back on it, and the rivet hole and everything is intact. So now I'm going to go ahead and get this safe, and we'll put the batteries in it, and we'll do a test and see what happens. Okay, so I got the transformer in, and as you can see, it's actually working. It's now oscillating. If I move this over by the source, look at, we now have a Geiger counter. So the only other thing I got to do is calibrate it. Well, two things I got to do is calibrate it. One, the headphones were working, but when I unscrewed it, this came completely off. So that's an easy fix, right? You just got to resolder the wire and put it back in, and I marked them, which one's positive, which one's negative. So I'll do that now. Then I can actually listen to the clicks. But I don't know if you can hear this, but you hear that? That's the oscillation at the transformer. Sorry about the people walking around upstairs, but maybe you can hear that. So that was the problem. That transformer let go. And of course the clip let go and the batteries corroded and all of that. So I'm going to shut this off, and I will let it discharge while I work on that, and then I'll discharge it manually, check that capacitor, and the next thing would be to calibrate it. I'm going to paint the inside of that case and put a new schematic in there. This video is getting really long, so I'm going to probably do the calibration and the rest of it later. You see I just got wires jumped here to do a test, but we'll go through that in the next video. So anyway, thanks for watching. I hope you found this interesting, and I hope it helped you to understand at least how this works. So thanks for watching, and we'll continue this video next time. Bye-bye.